Hi, my name is Walker Daniel, and today I'll be presenting my lab for oscillation. First and foremost, the goals for this lab was to create a predicted oscillation model using GlowScript and then compare this data to the observed data tracked through Tracker. And also we were supposed to compare energy changes as time progressed. A little preview for the answers or the results was that the position for the observed data had a shorter x position oscillation and longer Y position oscillations, and the total energy did not change. Here are some key concepts that are important for this lab. First and foremost, Newton's second law, net force is equal to the change of momentum over the change of time, which can be seen in this equation here. Next, velocity update formula, which relates the net force to velocity, which is seen right here. And then finally, the position update formula, which relates net force to position, as seen right here. Here's another key concept, which is the energy principle concept. And first and foremost, the change in energy of a system is equal to the work from the surrounding plus thermal energy transfer, which can be seen in this equation here. And then there's also multiple types of energy that can affect the system, specifically ours. First one is potential spring force, which can be seen with this formula here. Then there's potential gravity, which is seen right here. And then finally, potential kinetic energy, which is seen right here. Here is our observed video. And this was our initial data. First, mass was 0.402 kilograms, time was zero, position was this hard number to read, and then finally velocity was set at zero because the object started motionless. And then here is our graphs for both the x position and the y position over time. And as you can see, they're oscillating inversely to each other. This is my computational model. Um, this first little square right here shows a lot of initial data, which is just the same as seen in the observed model. And this part right here indicates the way to gather the files um, so we could compare both graphs. This is more initial data plus a little bit of formulas that we use to calculate kinetic energy, potential gravitational, and then potential spring, and then total energy. And then these bottom two are both in our loops, and it's just more equations to calculate um, each point for the graphs that I'll show you next. Now. So this top one right up here is my change in energy versus time. And as you can see, um, change in gravity, potential gravity and change of potential springs are inverse to each other. And then they also delta E remains at zero. And as you can see, these bottom two, our Y position graph shows that the experiment had much larger Y oscillations, and then um, and our experiment had shorter X oscillations. These are our potential errors. First is rounding error. Um, we were working with some pretty small numbers, and it was hard to get exact numbers. Difficulty tracking. I'm only human. I can only do as much as I can when clicking each point for the track. And then we didn't account for drag, which could have affected our um, experiment. And then finally, not accounting for other energy forms. There could have been something we didn't consider, and that may have caused some different oscillations. Here are my final questions and future discussions. First is, for your model system, is there energy principle satisfied? And yes, it is. As you can see in the photo, um, the energy change stays at zero, so nothing is created nor destroyed. It all is inverse to each other, and everything cancels out. And then also using the data you obtained in Tracker, make two separate estimates for the oscillation periods. And I did this um, by using both the observed x position graph and the observed y position graph, and I took the delta t of each spot or of three oscillations, and then found the average, which for the x position equated to 1.587. seconds per oscillation, and the other one using Y was 1.495 seconds per oscillation. And that's it. Thank you.